our third unit, which coincides with chapter 5, more or less, in your book. And so this is where we're going to spend our time today. Don't forget, tomorrow is your Unit 2 test, which goes along with chapter 4. So keep that in mind as we go through this. So as you can tell, there was a couple of intro videos, intro activities here. And so I would like to start off to just kind of assess where you all are at, give you a chance to assess where you're at as well. If you would, take a look here at numbers 2 through 5 in your packet and try them. See how it goes. And if we need to do a little discussion, a little cleanup work, we can certainly do that. So please try 2 through 5. So if I were just to say in general, the derivative of ln of something
is 1 over that something.
It's 1 over that something with the potential of,
The derivative of that something.
yeah, chain rule factor of times the derivative of that something. Guys, listen up, please. Here we go. So for number 2, I would say that this derivative would be 1 over that something times the derivative of that something. So that would be a fine way of putting it. Of course, there's some simplifying that could be done. Do you all get 2 over x? As maybe a final simplification. Maybe fine there. Number 3. This is where it's a little bit different. The ln is involved, but it's not involved in the exact same way it was in number 2. Isn't ln of x now kind of the inside of a composite instead of the outside, I guess? So I would say this equals 6, parentheses, ln of x, quantity to the 5th, times, what's the chain rule factor? 1 over x. So again, there's a little cleaning up and simplifying you could do with that if you so chose. Not really mandatory. We wouldn't really do a whole lot in this case.
Is it 1 over u du dx? No, ln.
It's 1 over u times du dx.
Okay.
Yep.
Oh, wow.
1 over u times u prime, or you could say u prime over u. There's lots of different ways to say it, but you've got a good one there for sure. All right, number 4. This time again, ln is featured, but this time like the main process is what?
Product rule.
A product rule, yes. So this would be 1 d2 plus 2 d1. Some obvious simplifying you could do there. You could even factor out an x cubed if you so chose, and you could even do a log condensing if you wanted. I mean, there's stuff you can do there. As to whether you do that or not, that'd be up to what form your answer needed to be in. So, how's this going?
Fantastic.
Any questions? All right. So then there's one last one in this sort of basic warm-up set. We were talking over here, this is like a box within a box, and then that whole thing is within another box, right? It's 3 functions composed together. So would you guys agree with me that the biggest of the boxes would be this ln? And the medium box would be this ln, and then the itty-bitty box would be the x squared. Oops. Like so. So the derivative of ln of something is just 1 over that something. So I would say that this is differentiating the green part. This would be 1 over ln of x squared. Make sense? And then the yellow part, I guess yellow was a bad choice. Let's see if it shows up. Can you all see that? Hey, there it kind of showed up. 1 over x squared. And then what's the derivative of the tiny box? 2x. So that's your chain rule there in color. And you could simplify that a bit if you wanted to. There's not a real pressing need for us to do that, but you could do some canceling and some multiplying and you'd be good. Okay, so I'd say fairly straightforward basic set with some complications and some variations, but do you have any questions there? Okay, so I think one of the things that's coming up next is this thing called logarithmic differentiation.
That sounds awful.
And, I don't recall asking for your opinion, Sam. So logarithmic differentiation is not something that's required on the VC test, and us getting pushed constantly with time and then chapel going 5 minutes late, this is my cue to say we're not going to talk about it. Other than to say, I wouldn't test you on this anyways. It's really, honest to God, like if you think logarithmic differentiation is the hardest thing you'll ever face in school or in your life, you're in for a rude awakening. Like, it's not that hard. It really isn't. But it's unnecessary, and we're pressed for time. So it is a valuable thing, perhaps, if you moved on to other bigger and better things. But we'll just leave it alone for now. If you're really curious about it and you wanted to come in and say, what was that thing about? More than happy to show you. Basically, it revolves around, do you know how to do log rules, right? Like the log of a product, log of a quotient, that sort of thing. Can you expand, contract those, and then deal with it from there? So again, not the end of the world, but it's going to take a lot of time and space. Let's go ahead and move on to number 7. Number 7 I want to take a little bit of time with, and this is starting to get a little bit into kind of your guys' commentary on what about that absolute value thing that shows up in these sometimes. This is a good example of that. So I'm going to start off by saying that if you are trying to find a derivative, this says differentiate. So if I was going to find f prime, one of the things that people will do, and it's going to be one of those things where, like, have you ever made a mistake, but then you made another mistake, and that sort of covered up for your original mistake, and you ended up getting the right answer? Or maybe you blissfully ignored something, and it was actually okay to ignore it. You just didn't know why, and it turned out that actually that wasn't a bad thing, and it all just seemed to turn out okay. People will do that all the time with this. What they'll do is they'll say, oh, I'm really uncomfortable with the absolute values, and so I'm just going to pretend like they're not even there. And I'll just mentally erase them or physically erase them and just proceed on as planned. Let's talk about the details of this, and we'll see how if somebody did do that, they would actually unwittingly be getting a good answer, but they wouldn't have any idea why, perhaps. Let's make sure you know why. Fair enough? Yes. Okay, so I am going to come over here and talk about cosine of x, and specifically the absolute value of cosine of x. And I'm going to define this, I think, in a way that you've seen before. I'm going to say that the absolute value of cosine of x is equal to cosine of x under one condition. If what? What would make this true? We'd say absolute value of cosine of x is just, in other words, almost looks like we drop the absolute values. If what?
If x is greater than 0.
Not if x is greater than 0.
Between 0 and pi over 2.
Oh, now we're talking, but we don't really have a domain like that, right? Because think about it, doesn't cosine's graph do this? Oh, sorry, kind of lagged there for a second. And so if cosine's graph does all that, isn't it constantly going from a positive value and then later on a negative and then back to a positive, so on and so forth? So how could I define this in such a way that I can say that the absolute value of cosine of x is just cosine of x? Under what conditions? It's always continuous.
It's always positive.
No, it's not always positive, because I can see down here sometimes cosine's negative. Say again?
Negative pi over 4 to pi over 4.
But now we're restricting ourselves to just one very restrictive domain. And what if my point of tangency is out there at 20? Now I have to reset all this. I want a really general approach, and this is going to seem super simple. What do you think?
Is it derivative of cosine?
Isn't it cosine squared?
It's bigger than 0.
The derivative of cosine. So if the derivative of cosine is bigger than 0, what does that mean about the graph of cosine? It's increasing, and do you see how right here's a place where the derivative of cosine is positive, and therefore cosine is increasing, yet the value of cosine is negative.
Maybe
You do the double prime, then when it's conquered, when it's negative, and then
No, that we may or may not be able to get there, but I would say we're way overcomplicating it.
You take the 17th derivative.
18th, I'm sorry. You were very close. Yes, ma'am.
If cosine of x is positive.
There we go. Yes. So we would say only if cosine of x happens to be positive for the particular numbers that you're looking at.
what? But you don't know.
I'm just saying if. You have to agree that there are parts of cosine where the y values are positive and parts where the y values are negative. And we could describe that maybe in a number of ways, but to me this is the simplest way. Why not go with the simplest way? Okay? So then we also have to acknowledge this could be true as well, that the absolute value of cosine of x could be negative cosine of x. Under what condition?
Cosine x is positive.
Not if cosine is positive, it's if
less than 0.
cosine's negative. That's right. Because if cosine of x is negative, to make it positive, you do the negative of it, getting the negative, negative, therefore positive. And this goes back, have y'all seen...
Weirdest news I've ever had.
It's the first time for everything, Santi.
That's borderline offensive.
Have you guys ever, I hope that you'd be honest about this, because, well, I hope you'd be honest about this. Have you ever seen this definition of absolute value? You ever seen that in any of your math classes ever? I showed this to you last year, so I'm starting to, this is getting a little shady now, because I know I showed you this very thing, maybe not with cosine, but
Yeah, I did not have you as a teacher, so.
so you should, I need to talk to your pre-calc teachers, because you need to see this in pre-calc. We need to see what they're doing with this.
Mr. Blake.
So this is so you know when you hear absolute value, people say, well, it's the distance from 0 on the number line. That's true. That's a good description. Or you could say it's the value of a number without regard for its sign or something along those lines. This is like a rigorous, actual, foolproof definition. Complicated for sure, but it's a precise definition of absolute value. And all it's really saying is, hey, if that number inside the absolute values is positive, then the absolute value of it is just that number. However, if the number inside the absolute values happens to be a negative number, well, then the absolute value of it's not just that number. Isn't it the opposite of that number? And, of course, the absolute value of 0 is just 0. Hang on one second, Forrest. And so do you see how what I wrote down up here, do you see how that's essentially using the same kind of definition with cosine of x, right? We're saying the absolute value of cosine fits this same pattern if we're doing the absolute value of cosine. Forrest, your question. Can you hear him? I'm having a hard time hearing. You're so soft-spoken. I'm really having a hard time.
How do you solve derivative of absolute values?
The derivative.
You would have to do a piecewise derivative. Okay, so I think you're getting way ahead of me here. Let me come back around to that, because I think you've diverged down this little path. I'm going down this path, and if you want to go back to this little diverging path, we can. So guys, here's the deal. The original question was, how do you find f prime if f of x is equal to ln of absolute value of cosine of x? Now check this out. I have to acknowledge, based on the definition of absolute value, that there are two cases here. One of them is f of x could equal ln of just cosine of x, right? That's if cosine's positive. Or it would be f of x equals ln of negative cosine, and that would be if cosine happens to be negative, right? I'm considering both cases in regard to the absolute value. This is me evaluating the absolute values. I can't just say absolute values go away, because that doesn't make any sense. You actually have to do something. This is me doing something. I'm evaluating the absolute values. Now check this out. This is where this gets kind of cool. F prime of x, well, isn't the derivative of ln of something just 1 over something times the derivative of that something? So you would get 1 over cosine of x times, what's the derivative of that inside?
Negative sign.
Negative sine. And can you see how negative sine over cosine would be? Negative tangent. Okay. So we get negative tangent right there. Then, if I come over to this other side, well, surely this will be a different answer, but it's not. Check this out. So this would be 1 over negative cosine. We still have to multiply by the derivative of the inside. What's the derivative of negative cosine? Isn't it negative sine? Also known as positive sine of x. So what's sine of x over negative cosine? It's the same thing that we got on the other side. So here's that happy coincidence that some people run into. When you're trying to find the derivative of ln of absolute value of something, you actually can proceed as if the absolute values aren't even there. Not because we just feel like it, it's because of a proof like that, right? Because that's just how it works out, and you can kind of prove it to yourself and say, hey, this does work. Question?
So that's always true?
If you're doing the derivative of ln of the absolute value of whatever, you can just mentally erase the absolute values and know that the end result going both paths should be the same, so just mentally erase them.
You have to prove it every time.
Nope.
Oh, jeez.
No, not at all. I didn't want to just say, hey guys, trust me, You know, when there's like a really easy way of proving it, right? It's super easy to see it as opposed to this like 1 hour long proof. So yeah, that's all.
I should just put a negative.
Okay, so okay, go ahead.
So
Yeah.
we've seen like absolute values and integrals before too. So how would we do that? Or are we just gonna go over that later?
So there's a number of ways to handle that. You might have to piece it out. Piece it out into the parts that were affected by the absolute values and parts that were not.
Okay.
So
there's I think there's one of those like on the actual like website, and so I just said like
we can certainly could look at that if you want, but yeah, oftentimes you just piece it out. Yeah, and hopefully there's not like 25 pieces.
let's
Yeah. All right, so Forrest, what if we wanted to do the derivative of the absolute value of cosine? Because you kind of asked that earlier.
So I'm guessing, like, do you have to write two answers? Like one
Yes. It's just like what you see above. You'd say d dx of absolute value of cosine of x, and then you just do the derivatives of the two pieces, right? This would be negative sine if cosine is positive, and it would be positive sine if cosine of x is negative.
It really confused me a lot. But,
Absolute value, would you guys agree with me that absolute value very often, if not every time, could be rewritten as a piecewise? The pieces being the pieces that were affected by the absolute values and the pieces that were not. Sometimes that would be pretty easy to do, other times that would be harder to do, but I think you could always do that to some degree or another. And that might make it easier. I don't know. All right, how are we doing?
Just
Okay.
amazing.
So we're going to switch gears to integrals, but it's going to be the same theme with LNs, okay? So again, in the intro video, you saw something about this, and hopefully this will go together nicely with what we have just been doing. Timmy is going to reappear for us, and I very much favor Timmy for much of this, if not all of this. So let's see here. Well, let me just give you a brief example. So, like number 2. This is where we're going to start talking a little bit more about fractions, and this particular unit, as you maybe would think, would have a lot of fractions in it. So, taking a look at number 2, you see a fraction, and this strategy, you know, like, I don't know if you would think this or not. Remember how in the past we've like tried to avoid fractions?
We want that to be a fraction.
We kind of do want it to be a fraction, and here's why. If I were to try to flip up, I'd get this. Can anybody tell me what's so wrong? Can you see it yet? What's so? Now it's a product, which may or may not be a bad thing. Like, think about this. What if we did the whole Timmy messed up the chain rule thing here? Let's think this over. Wouldn't you guys look at this over here and say that's a composite, right? I guess the other one is too, but maybe you look at tangent of x to the negative 1 and say that's composite. Is the derivative of the inside the other factor, Timmy? Timmy didn't mess this one up, did he? Isn't the derivative of tangent secant squared? For once in his life, he didn't mess this up at all. But now there's an issue with your exponents, right? Because you would say, well, all right, this would just go back inside. Wouldn't this be tangent of x to the negative 1 plus 1 over negative 1 plus 1? So you end up with this tangent of 0, which is odd but not necessarily terrible. That's terrible, right? Negative 1 plus 1 division by 0. We know we've created an issue. So I just wanted to tell you this up front here, and I'll tell you probably other times too. If you ever try to do an antiderivative of anything, and you end up with blah, blah, blah divided by 0, probably means you need to reverse course and consider, should this be ln? That's going to be your first hint, right? It means you made a mistake. Some of those other ones could enter, but most of the time, this division by 0 thing goes right back to ln, I'd say most of the time. So what I would say here is, since you've got a fraction, the first thing I'm going to ask myself is the derivative of the denominator the numerator? And the answer here is yeah. And Timmy didn't even mess it up at all. So if the derivative of the denominator is the numerator, the antiderivative will simply be natural log of the absolute value of tangent of x plus c. So it'd be natural log of the absolute value of the denominator plus c.
Why is it the absolute value?
So why is it the absolute value? So you cannot do, if you have natural log of a has to be greater than or equal to 0, does it not?
Yeah, it
You
does.
can't do ln of 0, and you can't do ln of negatives, right?
Right.
And so what we do is we put the absolute values in there to allow us to consider both a positive input or a negative input. And that's going to become really important when we start solving differential equations. So at this point in the game, like if you didn't put absolute values, I'm probably going to just remind you and say, hey, there should be absolute values there. I want to create that habit for you. When we get a few units down the road doing some differential equation things, that's going to at times be super key. Okay, because we want to be able to allow for both negative and positive inputs based on whatever the solution curve would be, which gets us into differential equations. So think of it as building a habit right now, I would say. Okay, so why don't you guys try out the other ones we got here, 3, 4, 5, 6. Definitely try out 3 and 4. Try and make these a little more visible. 3 and 4 I would put firmly in the, assuming you know how to handle Timmy and his perpetual mistakes, I put 3 and 4 into the fairly easy category. 5 and 6 would be in the tougher category. So I'll tell you what, why don't I just zoom in a little bit better on 3 and 4. You can see some of you are about to pull an eye muscle trying to see those. There we go. So there's 3. You're like, I would be doing the same thing. What's up, Forrest? Yes, sir. So there's a number of ways. So here, let me finish it. So I was showing you this to show you a way that does not work. I want to show you this and say, if you try to do it this way, this will lead you down a bad path. You'll end up stuck. Right, so what I'm, I just want to point out that when you try to do this, you end up with a 0 exponent and a 0 denominator. That's an issue. So I would go back to it. So we want it to be a fraction.
So you do,
There should be a factor.
No, we're not differentiating. We're not trying to find the derivative of this. We're trying to find the antiderivative. Yeah. So whenever you have an antiderivative where the integrand is a fraction, what you want to ask yourself is the derivative of the denominator equal to the numerator? So the derivative of tangent is secant squared, right? And so since the derivative of the denominator is the numerator, you're going to end up with a natural log for an answer. It'll be natural log of the denominator. So I would say ln of absolute value of tangent plus 6. So let me prove it to you backwards. So we're looking at it. Couldn't I take this and differentiate it to check my answer? So check this out. Derivative of natural log, and I'll just consider the positive case just for the sake of time. The derivative of natural log of tangent of x, wouldn't this equal 1 over tangent of x? The derivative of ln of something, the derivative is just 1 over that something. Times the derivative of the inside plus the derivative of tangent.
The antiderivative of x squared plus 3x
Compare our original integrand.
minus 7.
The derivative of the chain rule.
Okay, Jack, I'm going to teach you something that you're trying to trick me.
tangent x equals to this one.
The derivative of that tangent is 1 over tangent
And then
times the chain rule factor.
Do you have to do So I probably can.
No, because it's only 2 functions composed. The 2 functions are ln of something and the inside is tangent. So there's only 2 functions composed. So your chain rule will just have 2 parts.
Okay, so there's like, it's, 1 over
Are you watching your intro videos? You need to watch this.
Okay.
You see those coming up, don't you? Like on your Schoology?
Yeah,
You need to watch those. That's why you're feeling lost.
Okay.
All of this is explained in intro videos. We just don't, honestly, I don't have the time to, at the start of class, go over the basics of hey, here's the rule and all that stuff. And there's just no time. So you have to watch the intro videos.
Honestly, I just
not going.
That's fine, but I'm saying that the intro videos will probably help us out to kind of warm up. You're like, oh, it's that LN thing. I did this last year. I can do it. Versus just showing up cold.
You did the right thing.
I'm not. I get it. I'm just saying, you can just say, if you want to feel less confused when you're in class.
Oh my god.
Take the rewrite.
Yeah.
You're welcome.
Multiply.
All right.
Or divide
So on number 3, Timmy messed up a little bit, right? So what I'm thinking I would do with this is ask myself, is the derivative, or excuse me, is the derivative of the denominator of the fraction the same as the numerator? And the answer is not quite, right? He's off by what factor? 2. So to fix Timmy's mess up, what I would do, this is my original, I would multiply the inside by a factor of 2, but then to balance that out, what do I have to do? Divide by 2, or multiply the outside by 1/2. Same thing. Okay, you could do this full on with substitution. You'd make your u your denominator. I just think that it's quicker to do is like, what's missing? A 2. All right, 2, 1/2, done, right? Okay, so then to wrap this one up, we would say this is 1/2 natural log of absolute value of the denominator plus c. And there you go. Okay, any questions? Okay, number 4. Once again, Timmy has made a little mistake. What is he off by as far as numerical factor? 3. So I'd go times 3. Now it perfectly fits the chain rule pattern for natural log. I also have to multiply the outside by 1/3 to balance that out. Did you guys get 1/3 ln absolute value 3x plus 2 plus c?
Heck yeah.
Okay, of course you did. Very good. Did anybody venture off to 5 and 6?
I did 5.
5? Okay, so let's look at that, and then maybe we can talk about 6 together. So one thing I notice about 5, and really honestly also about 6, this is a very specific case, and I think dealing with integrals and antiderivatives is often about recognizing a form, recognizing a pattern. So did you notice that in 3 and 4, did you notice that the degree of the numerator was less than the degree of the denominator?
Yes.
So that means that ln is a possibility right off the bat. It might be natural log. But then when you look at 5 and 6, did you notice that it's the other way around? The degree of the numerator is actually bigger than the degree of the denominator. And so in these cases, we are pretty exclusively going to do one thing to get these into a better form, and that's division. Sometimes that division will be super easy. Sometimes it'll be a little bit tougher.
It's easy.
Here's one, like number 5 is the simplest version of division, right? If you wanted to, you could rewrite this as this. You basically could just divide an x out of everything, or you could flip the x up and distribute it, right? The bottom line is once you simplify it, don't you get x plus 3 minus 7 over x for your simplified integrand?
I have no idea.
So I kind of like mentally will just split up the numerator over the denominator, do some quick canceling, and that's pretty straightforward. Why on earth would this be in the little section on natural log?
Because 7 over x.
Yes, the last term. Otherwise, we maybe wouldn't know what to do with that. So it's a couple of power rule type ideas. So this would give us 1/2 x squared plus 3x. There's the 2 power rule concepts. And then the last one, as you all said, that's natural log. So b minus 7 natural log of absolute value of x. Don't forget your plus c. So sometimes you have to do a little simplifying, a little bit of work on the front end to get it to a better form. Number 5 is an example of that. So did anybody venture on to 6? So with 6, it's division again, and I would favor that. So take a minute.
I did not do
Synthetic division. So with number 6, we can't just split the numerator up over a binomial and get the same kind of canceling. And so I would use, you could do long division if you want. I prefer synthetic division, but you do have to do division. Whenever the numerator's degree is bigger than the denominator's degree, division is a likely strategy. So I'll get this zoomed better here. Look at number 6. It's right there.
Probably.
Oh, it's a negative. What do you do with like? When you go to 0 in the second to last term, and then the last term is 7. Did I do that right?
It's I don't know. Let's find out.
Yes, you did that right.
Let's
You
find
did
out.
that right. I was confused too, but then I looked
So-
at what Logan did, and I was like, oh, that makes sense.
So I usually do synthetic division like that. That's my divisor. You always do the opposite of the number in the divisor. And then, do you all recognize that squared is missing?
Yes.
So it'd be 1, 0, -4, and 7 for your coefficients. Don't forget if one term is missing, put a placeholder in there. So then if you remember, what you do is you bring down the 1. So you start your cycle here. -2 times 1 is -2. You add those up, you get -2. You multiply those to get 4, and there's that 0 you just said. So there's 0, you multiply to get 0, and your remainder is going to be 7. So what you can then do is you can rewrite this as, it would be x squared minus 2x plus 0, but I'm not going to bother with that. And then you write your remainder as a fraction? That's right. So it'd be plus 7 over x plus 2 dx. Okay, so then that is in a much easier form for us to handle. So it's basically 2 power rules and a ln. So I would say 1/3 x cubed minus x squared plus 7. Natural log absolute value x plus 2. Don't forget the plus c. So again, sometimes people will wonder, when do I do this? When do I do that? If the degree of the numerator is bigger than the degree of the denominator, it's likely that some sort of division, synthetic or otherwise, would be warranted. Thoughts or questions? Okay, so let me just turn you loose on this last one. Got just like 6-7 minutes left. It's number 7, dealing with area. So I do want to tell you, I said no calculator here. I do want to tell you that the graph of this function over here on the interval 1 to 2, the graph is always positive, right? It's always above the x-axis because it does say find the area of the region. So if some of it were below, we get some weird stuff going on. None of this graph is below, it's all above. So try to set this up to find your area from 1 to 2. From 1 to 2. So that integral would be the integral from 1 to 2. Of the. By the way, I hope this isn't lost on you. I think you know this. Isn't the integrand essentially base times height?
It is
It's nothing magical here. What is base times height?
the area of a rectangle,
The area of a rectangle, right?
which is where we started.
Which is where we started way back in chapter 4, unit 2. It's still, finding the area is still just the base length times the height. We're taking the bases and we're making them really, 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 really small. And the heights are just whatever the y values are. We multiply those two together, add up an infinite number of infinitely skinny versions of those rectangles, and we get the actual area. Okay, so anyhow, did y'all simplify it like this?
Yeah.
Just do some quick division, divide the x out of all the terms. So when you do that, you should get 1/2 x squared plus natural log of absolute value of x, evaluated from 1 to 2. You plug in a 2, and what do you get? You get 2 plus natural log of 2. And by the way, at this point, I can drop the absolute values because the absolute value of 2 is just 2, right? Minus, it would be 1/2 times 1 squared plus ln of 1. And ln of 1 is? 0. 2 minus 1/2 is 3/2. Do y'all get 3/2 plus ln of 2? Okay.
Yes.
And obviously approximate that with some decimal, but that's a great answer.
If it wasn't like
I mean, you were never wrong. I was wrong.
can't you simplify?
You were
Like
never
L 2 minus L
wrong.
3 is no L 2 over 3, right?
Yes.
Okay, I was just making.
Very true. And that would be those log skills. Like if we were going to do that logarithmic differentiation thing,
Okay,
be able to do that kind of stuff, that would make a difference.
okay.
Okay, so any other questions?
No.
Okay, so tomorrow's your test. You ready to go? Knock it out of the park. Bring your extra practice work for a quiz grade tomorrow. Do I have everybody's test corrections?
Yeah.
I've kind of been waiting to get all those in before I put them in the grade book, but I'd rather do it once than a bunch of different times. Okay, see you guys. No, I have AB.
Thank you very much, Mr. Anderson.
Absolutely, thank you.